at EFRIB, which is the Academic Specialist for Nuclear Science and Graduate Student Success. Long title, so he's actively involved in research, but also mentoring graduate students and also high school students. So with that, I will let Pablo start exactly on time. So take it away.
Thank you so much, Jason. I'm so happy to have powerful friends in committees. So can everybody hear me okay? Yes? Okay. If for any reason you cannot, please let me know. An absolute pleasure to be here. This is my first colloquium, so I am more scared of you than you are of me. But I'm very, very glad that I have this opportunity to do this here. My talk is called Life is Too Short for Slow Computations, and I'm going to be talking about dimensionality reduction to speed up things every time that we want to calculate things, both from the theory side, but also if you have simulations for tuning and controlling experiments. This is the outline of what we're going to discuss today. I'm going to give an overview of nuclear physics, because this is a colloquium, not a nuclear physics talk. Then we're going to dive right into the dimensionality reduction part and how does it works, and I'm going to showcase some of the applications we have been doing. I'm going to close the talk with very important points about using these tools to lower the barrier and make science more inclusive, and then I will give you a couple of takeaways in case I bore you to death in the last 40 minutes. A very important disclaimer, well, two important disclaimers. The first one is, it's kind of ironic that in a talk that is about dimensionality reduction, I have an insane amount of slides. These are not meant for you to take all the information here. I have that QR code that you can scan now, and I will give it again at the end of the talk. The idea is for this to be a source of materials that later on you can go look for something that could be applicable to your problem, and if you're interested, you can send me an email and we can start collaborating and doing things together. That is the first part. And the second part is that I'm going to be presenting a lot of results. This is not something that I have done just myself. This is work that is done in teams with a lot of people. So if you are any student, postdoc, faculty, or anybody, and you see this and you're like, wow, do I need to be doing all of those things right now? No, not at all. I am only here because I was able not to stand in the shoulder of giants, but to make good things with people that are nice and fun to work with. Okay, so nuclear physics in not 3 minutes, maybe like 5. You have probably seen the periodic table, the chemistry periodic table. You have your atom that has a nucleus and the electrons flying around, and we arrange the elements depending on how many electrons they have. We like to count them that way. We don't care about the electrons, mostly, in nuclear physics, so I'm only going to focus on the nucleus. In the nucleus, you have a number of neutrons and a number of protons. And if you arrange this thing in a different way, you get to the nuclear periodic table that now shows different elements for different compositions of neutrons numbers. For example, I can talk about carbon-12. From the chemistry perspective, carbon is just carbon. It has 6 protons, and then it will have 6 neutrons. But in the nuclear periodic table, I could talk about the isotopic chain of carbons, in where I have many carbons that might have many different numbers of neutrons. The ones that are in black are the stable isotopes. Those are the boring ones. We have studied a lot of, there's still things to be discovered there, but we have studied them to death. What we are interested in is in looking at the rare isotopes. Those are so far away from stability that are really hard to produce, and that contain information that have never been explored before. And that's why we built the facility for rare isotope beams. That is a nuclear lab that is in the middle of nowhere in Michigan, but a fantastic place to work. I am extremely happy there, and it's not because I'm getting paid to say that. To the point that I bought you stickers, if you want to have stickers to put them in your laptops and everywhere. I asked ChatGPT to produce this image. This is how I feel about the place that I work on. We built this machine to be able to venture into this land of rare isotopes that nobody has ever ventured before. And if you're starting to feel a tingle of excitement about these things, there is a movie coming, hopefully by the end of the year, that is about the story of EFRIB. But more than the story, it's about the people that make the facility. It's going to be called Rare Connections, and there is a teaser QR code, and you can start looking at the first 3 minutes of what Agnesh Moxie, who is the director, is cooking. Okay, so now that you have built the huge machine, what things can you do about nuclear physics? There is a lot of stuff, so let me break it down. Some big questions that might come up about this topic. Where do heavy elements come from? So if you look at how stellar fusion works, in many models you will stop at iron, and then you ask yourself, but I see gold, and I see platinum, and I see uranium, so where these elements were made of? That are still in debate, but one of the leading theories has to do with something that is called the rapid neutron capture process. Basically, you bombard isotopes with a bunch of neutrons in something like neutron star mergers or supernovae. Questions from structure. If I start deviating a lot from stability, what happens to the internal structure of the nuclei? How do protons and neutrons form the shell? I'm going to find interesting structure like the form nuclei or halo nuclei or bubble nuclei. Questions about neutrinos. What's up with them? They're just weird, and things don't seem to agree exactly with the standard model that we have. And we're not sure, for example, if they're on their own they are their own antiparticle. And nuclear physics has a lot of input to be able to that you need to calculate to be able to say anything about those experiments. And finally, the reason why we sell these to the public and we say that we're useful, can we do useful things out of all the discoveries that we're doing? Now, you want to study all of these things, and it's really, really hard. And I'm going to boil it down to two main reasons. The first one is, if you're thinking in terms of a game, the rules of the game are very unclear. Copying an analogy from Feynman, this is similar as if you were trying to understand how chess game works and what are the rules for chess. And you can watch the game one instant at a time, and it's very dark, so you don't see very well what is happening. And half of the screen doesn't work because neutrons usually don't react electrically with anything, and you're wearing sunglasses. So this is how doing nuclear physics feels like. You're trying to infer the rules of the game until under all these hindrances. And the second problem is the emergence of complexity. Even if you were to exactly know how these things play off, no way you're going to be able to predict things. And as an example, I'm putting the game of life, that is a game, basically, that has 3 very simple rules, and out of those simple rules, you can build things that are just unbelievable. So knowing the rules of the few will not necessarily tell you how the big is going to evolve. So bottom line, it's just a wonder that any of the things that we're doing even works. And that's why you have to have a very strong theory, observation, and experiment cycle. Now, let me give you a final example, diving deep into what this cycle might look like at FRIP. We have all this interest. Let's say that I pick astrophysics. And because we're talking about it, let's say that I pick the R process. I want to understand how that works. I need a lot of information from a lot of measurement and from a lot of nuclear theory. I need to be able to calculate things like lifetime masses, capture rates. Let me focus on masses. I end up having a lot of different theoretical models that can predict the masses of nuclei. And if I run my R process calculations using 2 different models, I already have different answers. So then I can say, well, let's go and try to build new experiments so we can constrain those models better. There is a ton of experiments that you can make, and there's a ton of isotopes that you could make the experiments on. And on top of that, you want to connect with the people that are doing observations, the people that are measuring gravitational waves or the radii of neutron stars with NICER. You need to incorporate all of these together to be able to better learn the rules of the game. And my claim, and I couldn't resist to put a heart because we are in St. Valentine's Day today, is that a big part of the heart of that process has to do with statistics and advanced computational techniques. And that is what I'm going to be talking about today. Now, why statistics, you might be asking. I'm going to put this as an example, the Monty Hall problem. How many of you have heard of this problem? Okay, I see some people that have not. Those of you who have, don't make any opinions on what I'm about to say. Imagine that you have a situation where you have 3 doors, and I tell you behind one of these doors there is a magic golden ticket for a free NSF proposal without having to go through reviews. You want that ticket, and behind 2 of the doors there are goats. So you pick one of the doors at random, and then the host of the show tells you there is a goat in number 3. For those of you who have not seen this problem before, should you change doors or should you stick with the door that you had? You had 10 seconds to think about this. How many of those that do not know about the problem, how many things you should change doors? How many will stick with their own door? Turns out, if you run the statistics, some seems counterintuitive at first, but changing doors gives you twice the amount of chance of getting the golden ticket. So you see how making a decision not based on rigorous statistics will give you half the chance of getting something as amazing as a free proposal. And that's what we want to avoid. For all of you smart cookies that said that you did know about the problem, anything changes if the host doesn't know where the ticket was whenever they pointed out where the door is. Think about that. We don't have time for that in the colloquium, but it's a nice thing to reflect later. Second, machine learning. Imagine that we're in the classic machine learning homework of trying to write an algorithm to classify the digits. I want you to think for 10 seconds again, if you didn't know about neural networks, let's say 50 years ago, 40 years ago, and you wanted to write a code that explicitly does this, how will you do that? Think for that. 10 seconds. It's really a non-trivial problem. It's just that we have seen it beaten to death so many times with neural networks. Let me show you how I will do it. I go to ChatGPT and I say, hey, could you write a Python code that downloads the data, uses TensorFlows, and trains the thing and shows the performance? And I solve the problem in 30 seconds. I'm not saying let's solve all the problems with ChatGPT, but there is, as many of you are aware, an immense amount of potential that we can draw from these things that your brain alone will not be able to figure it out. So the theory experiment cycle that I was talking about actually in reality looks more like this, at least in nuclear physics. We are using a lot of these tools to really dive into that very complicated nuclear physics that we want to explain. Otherwise, there is no hope that we're going to be able to advance any further. And this is not just me saying it. We as nuclear physicists have this tendency of gathering every 5 to 7 years to write down a document that says these are the things that as a community we think are important, and some of the things that we said are important has to do with quantifying uncertainties, using statistics to really know what is going on, and the same with machine learning. And because I have powerful friends beyond Jason in committees, I was able to be captured in a picture in the long-range plan with my friend Kyle. Because of this importance, we were able to also, through more friends, run a summer school this last summer at EFRIP that was just focused on that. Uncertainty quantification and machine learning development in nuclear physics. And I'm going to be given the drive for all the resources. So many of the things that I'm going to be talking about here can be further explored down there. OK, that was a nice 12 minutes introduction to nuclear physics. Let's go to the dimensionality reduction part. So here's how the thing looks like from an applications perspective. I have some experimental data, and I have a model that I'm going to call F. And my model depends on some parameters alpha and x, whatever is the quantity that I have in there. We don't want to just fit the parameters of the model to reproduce the data. The goats are watching us. We want to be able to make a full uncertainty quantification on our predictions. And usually we do that through things like Bayesian statistics. You might have seen this equation before. I'm not going to go into super detail, but this is the Bayes theorem that tells you the thing that you want is comprised out of things that you can actually build. The likelihood, basically how the data came to be, and the prior, which is all the information that you have previously from the data that you're analyzing. Now, the problem is that if you do want to explore this thing very, very well, sometimes you might need to evaluate your model, let's say a big number, 5 million times. And if your model takes 1 second to evaluate, it will take 2 months to evaluate the entire thing 5 million times. And if it takes an hour for each evaluation, and there are things that take an hour, for example, nuclear dynamics or evaluating potential energy surfaces for fission, you're going to be there for half a century. So this is not feasible. We need to do something about it, and this is where the butter mentality comes in. I want to grab something that I like, and I want to replace it by something that is an approximation that contains some of the things that I like, for example, in this case, that it can calculate what I want, removing parts that I do not, that in this case is it takes forever. So I want to replace the butter by I cannot believe it's not butter. And in this talk, I'm going to be mainly talking on the first part about building emulators for my physical models. But at the end, I'm also going to mention some techniques that you can use to emulate your posterior distribution itself. We can treat random variables and their distributions as high-dimensional objects that I do want to reduce their dimension to be able to calculate them quickly. This method can be data-hungry. So for building these things, we are not replacing high-performance computing. We're actually using it to be able to go through the entire process. This invites us to think about a change a shift in the computational paradigm that we have been having so far. As an example, some centuries ago, Newton was sitting, he was looking at the apple fall, and then he concluded, obviously, everything is attracted to everything through a gravitational constant. He was able to figure it out and then explain, predict, and do everything he wanted to do by pen and paper and a lot of patience. Now we're in the 21st century. This is us trying to understand nature and all the weird things that happen in there. And we have very complicated equations. They're not like Newton's equations. And we do all our calculations through high-performance computers, or in the case that they're not as expensive, our own laptops. And we're able to make our models to explain, predict, and build. This is where we're going to stick the dimensionality reduction part. So instead of just jumping to do calculations, the idea is, can I build with this equation these reduced order models for both my physical simulations and for the probability distributions themselves, such that once I have trained them, and no, they do not all look like neural networks, but I just want to give the idea of what is happening here. Once I build these things, I can deploy them in very different avenues. For example, commodity hardware or cloud performance computing, which then we use to make these calculations. And the reason why this is important is if they are fast enough that you can deploy them in a cloud environment, then everybody can do science, and we get closer to the vision that my friend Kyle has, in where we approach a future where every model is not defined just by parameters, but by posterior distributions that are constantly updated as new data becomes available. We want to move towards this, making this process of data to model to prediction streamlined as easy as possible. So how does it work? Let me explain it using the scattering differential cross-section that I was showing for those of you who know what that is. For those of you who do not, doesn't matter. I have a set of equations. I'm going to call them f of alpha. I'm trying to solve for those. They can be differential equations, simulation, who cares? I have a black box code that some poor grad student wrote 15 years ago, and nobody understands how it works. And I have my control parameters, which you can think of them as the rules of the game for my own simulation. And I run them through the code, and I obtain my observable, the thing that I'm interested, the cross-section of neutrons on calcium or whatever the heck I'm after. If you were to open this box, you will see that the code is calculating, in this particular example, the wave function for many partial waves of the neutrons, and it's trying to combine all of those and giving you a final answer for the cross-section. This might have, and I'm making up this number, 5,000 variables between the number of wave functions that I have and the grid spacing that I have for each one of them. The idea of a reduced order model is to build something that can bypass that very expensive calculation, obtain something that is very similar, but handling order 100 variables, not 5,000. And if you're able to do that, at the end of the day, this approach is going to be much faster for the same accuracy. We are going to quantify that by something we call the CAT plot, the computational accuracy versus time plot. And the goal is that the reduced order model will have a much better trade-off between accuracy and speed than the high fidelity solver itself. How does it work? It's two very easy steps. You need to find good reduced coordinates for your problem, and then you need to find equations for them. As a physical example, imagine that you have a brick. If you have your brick and you want to describe your brick correctly, you need to quantify or make equations for what is happening to each one of the 10 to the 24 atoms in the brick. Nobody does that. We say, if I want to describe the dynamics of the brick, I might be able to get away with just 6 degrees of freedom, 3 translations and 3 rotations, and I'm done. If the brick hits something and breaks, I cannot describe it with these 6 degrees of freedom, but I could improve my description on new coordinates that describe the part that I'm interested in. And now I need equations for these 6 degrees of freedom. I can just write the Euler-Lagrange equations or Newton's equations, and I will obtain how these things evolve in time. The same thing happens for what I'm about to tell you, which is called the reduced basis method. It's one of the things that you can do for modular reduction. And the idea is I'm going to find my coordinates by analyzing a handful of original or high fidelity solutions, doing some principal component analysis. I will explain that in detail in a second. And then we need to find equations for them. We're going to do that mostly through what are called Galerkin projections. This is Boris Galerkin. It's the same chill dude that is in my shirt. And I can tell you a story on why we are so obsessed with this friend. He's going to be all over the presentation. If you want to understand why this even works, because at the beginning it's kind of anti-intuitive, you can ask me after the talk. This is a fantastic question for when we finish the colloquium. Let me give you an example. Quantum harmonic oscillator from quantum mechanics. I have my Hamiltonian, this operator, this depends on my variable alpha, and I'm trying to find the solution. The solution is going to look like that for a fixed value of alpha, and I really, really like to think functions as vectors. I can discretize my space and then think that my function phi is just a very long vector in a very high dimensional space. Now, if I were to solve this problem for many alphas, I will obtain many long vectors that are living in that high dimensional space. And now look at this very cool animation that I made. If I were to solve it for a continuous value of alpha, now I get a solution manifold or a solution curve. Those are the trajectory that that vector is tracing in this very high dimensional space. The idea is that even though the vector itself lives in a very high dimensional space, the trajectory can be approximated by a very small manifold, plane, subspace, however you want to call it. And that dimension in this drawing is 2 in comparison to maybe 300 numbers that I was using to track my solution. These 2 directions on that plane is what are going to consist of my reduced bases. So if I were to write it in terms of equations, I'm approximating my function phi by a linear superposition of these 2, which are the 2 reduced bases that I'm using. And you can obtain this by using principal component analysis or singular value decompositions, which are fantastic algorithms that we have developed in the last couple of decades. Once I have that, I need to be able to create equations for my coefficients. I rewrite this equation as an operator, f, acting on my function phi equals 0. The details don't matter. Once you write that, you make your projections, and you end up obtaining 2 equations for 2 coefficients, and you're done. Now you have your reduced order model. How does it work? Here's an animation that is much better than the previous one, because I had more time to do it. This black curve is showing the harmonic oscillator as you're changing that value of alpha, and the dash curve is approximating it just by the linear superposition of these 2 terms. The coefficients are being found by doing the Galerkin projection, and I hope that you all can agree that this is doing a darn good job. It's a not very interesting problem because it's the harmonic oscillator, but this gets at least the explanation of what is happening. To be able to know if your problem is amenable to this type of dimensionality reduction, you can visit the PCA doctor, and she's going to tell you if the singular values of a handful of solutions are decaying exponentially. That means that you're in very good hands, and you're going to be able to reduce the dimensionality of your problem in this way. There is a ton of resources, and as I said, you're going to be able to check this later in more detail that you can go through to find ways of doing this. In particular, the one that I want to highlight is this dimensionality reduction Jupyter book that a huge amount of people, me included, have been putting together. And it has examples with codes, nice illustrations, and equations, and explanations, and everything. And the next person that contributes to this could be you, because this is a community-driven approach. In particular, I want to highlight Megan Campbell, who is sitting in the audience. She's a high schooler from here, from St. Louis, and she has been making staggering contributions to this Jupyter book. So you have your own expert on modular reduction here in St. Louis. And I'm going to talk about that a bit more at the end too. Okay, let me show you some applications because nobody cares about the harmonic oscillator. Density functional theory, some serious stuff that we use to model nuclear physics. In here, basically you say, solving my nuclear problem by tracking what is happening to every proton and every neutron interacting with all of them is too hard. That is marble physics. That means I need to take them as marbles that are interacting. Saori and Maria do that, and they are heroes for that. For now, I'm just going to treat my nucleus as a blob, and every proton and neutrons interacts with the blob in kind of an average way. Still, the equations are awful. There are nonlinear equations that you need to solve for each one of your particles, and all of these things that I have in here in purple are parameters. So you say, well, let's give it a try. You visit the PCA doctor, and if you see these green lines, those are the singular values decaying from the density functional theory applied to calcium-48, and you're like, oh, we're in business. This is part of a paper, the first paper that we published on this, showing this is kind of useful for a broad set of problems. So we went and we applied it to DFT. And in density functional theory, one of the things that I want to showcase is that the thing is extremely accurate. This emulator only trained on these 4 stars, and it was able to predict everything everywhere else. And I had a very hard time trying to convince the referee that we were not cheating, because they kept saying, like, this cannot be. And I'm like, but I'm not training on that. I'm training on the high dimensional functions on the background. At the end, I think they got it, or they just say yes. So we got to not annoy them anymore. And the third thing is that it's very, very fast. We were able to do serious density functional theory calculations in milliseconds, which is 2-3 orders of magnitude faster than the original code that was working with this. Second application, relativistic mean field, is another type of flavor of density functional theory, in where you have this interaction between your nucleus and some fields that are produced by the nucleus. So it's a nonlinear problem you have to solve iteratively, and it takes a while. These are the hardest equations that I'm going to show you, and the reason why I want to show you is because in here we have the Dirac equations, and my dog name is Dirac, and I always try to find an excuse just to show him in one of my slides. So you have the Dirac equations. All of these things in here are parameters. So what do? You project your equation with Galerkin, pew, 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 pew. And now you have your projection equations. Everywhere where you see fields and wave functions, you substitute them by the reduced basis. This is how the principal components of the reduced basis look like. And then you're done. You can make the goats happy because you can sample for your Monte Carlo studies with Bayesian analysis 5 million samples on my personal computing in a single day, which was a speed up of between 1,000 and 20,000 times faster than the high fidelity solver that we were using. So we were very happy. We're able to calculate actually observable things, masses and radii of different nuclei. One of them in particular, the radius of TIN 100, has not been measured, so this is kind of a prediction. At some point, it should be able to be measured at FRIP, so we will see if we did our homework correctly or the goats are going to be angry at us. Third application, neutron stars. Turns out that you can connect what you do in nuclear physics with the properties of neutron stars through what is called the Tolman-Oppenheimer, the same from the movie that you probably saw, Volkov equation. And this tells you a property of the masses and radii that you expect neutron stars to have. And different curves in here are going to be mapped depending on how are the rules of the game for your protons and neutrons interacting through nuclear physics. So if you play along with the rules and you start trying to solve the equation for different values of the parameters and the initial pressure, you end up obtaining something that the PCA doctor is not very happy about. How are you going to combine these things in a way that makes sense? Well, if you rescale them, and that is a trick that we had to play at that particular place, you can actually combine them, the singular values decay fast, and you're able to do an emulation and that it actually works. This is an ongoing project with a bunch of people, including a team from Los Alamos, and here we have cosmonaut Galerkin in his suit. Another application, reactions. So we started developing this software for the basically smashing targets, protons, neutrons, or on other nuclei into nuclei, and that is extremely important for a lot of things, including FRIP. The idea basically is that you shoot your particles at a target, they bounce back or interact in some way, you measure that, and that gives you information of an internal structure of your nucleus. This is my equation. The details don't matter. What I want you to have is that in here I have my potential. It depends on alpha. It's the rules of the game. I want to be able to make this type of Bayesian studies. So we created this software with the band collaboration. Those were the people that were paying for my lunch until December. And it's called the Reduced Order Scattering Emulator. And this awful thing is the explanation on how the emulator works. But here's the nice thing. You do not need to learn about this. If you don't want to, you can. But the idea that this is a user-friendly focused software is that you can just use it for making the calculations. This is a realistic cat plot that I was talking about. In blue is the high fidelity or traditional way of solving things. And in different colors than blue is the reduced basis method. And you can see that for a given accuracy, the thing is like hundreds to 1,000 times faster than the high fidelity calculations. And we are able to make our uncertainty bands, and the goats are very happy. This is particularly important for us because for FRIP, many of the models that we're using to calculate, extrapolate to the land of rare isotopes, they were calibrated to stable nuclei. So we're not 100% sure that the thing is going to work. It would be nice to have uncertainty bands, and that's why the community itself is claiming that this is important, and we, as dimensionality reduction people, are trying to provide the best to help them. So this is a software that you can install and play if you're interested in this type of things. And future directions include many things that I'm not going to go over detail. 5, application, dynamics. You can evolve things in times with this idea. In this case, I'm showing the harmonic oscillator again, but evolving it in time. And what happens is that in the original space, you have the evolution of a very high dimensional object. But if you do your projections, you end up having the evolution on a very small subset of coordinates. It's the exact same idea that we were discussing. And you can find the details on this in the book if you're working with time-dependent problems. This is very similar to something that is called dynamic mode decomposition, and I'm just throwing the name over there in case you have heard about it or you want to go and learn about it, because it's a very cool technique to, in a data-driven approach, build these reduced order models for time-dependent problems. Further, in the dynamic part, we have this amazing undergrad student. We're so lucky. I don't know how we get so many talented people. He has been working on something that goes beyond the reduced basis method and starts tapping directly into neural networks. This is an amazing framework that people from the other Washington University in Seattle have been building. And the idea, this is called the neural implicit flow, and it's something that can learn from very choppy data that is highlighted on the right for my stimulation from density functional theory. Is the same equation that we were looking at. It can learn something that sounds like magic, but it's called super resolution, in where you end up obtaining, by the time dynamics, information of what is happening in a smaller scale. And the idea is that it will also run much, much faster than the time-dependent problem that we're trying to solve. Aaron, which is the undergrad, was able to get an award for his work with us, and that's the whole reason why I do physics, so we were able to go and have a nice ice cream and celebrate together. This neural implicit flow comes from the group of these two folks that I strongly, strongly recommended that you take a look if you're interested in many of these things. They have a book that is amazing. I am president of their fan club because what they're doing is just incredible. And you see that they have the same philosophy. Well, I learned from them. So the idea is you need to discover good reduced coordinates for your system, and then you need to find the equations of the models that are going to evolve those coordinates as you change time and parameters. Now I'm going to talk about 7 application. This is something that we're calling the black box Galerkin, and I'm going to compare it to vintage Galerkin that is sitting here in this vintage model. What I have presented to you, you need to find your reduced coordinates and find the equations in these ways. But this requires that you have access to your differential equations. If you have something that is a black box, that you really do not want to open the code, or you have an experimental setup, you're looking at a beam that is passing through magnets, and you do not have an equation that tells you exactly what is happening, you cannot do directly these type of things. There is some technicalities that even if you have the equations, certain things will preclude you from making a good emulator. What we're trying to do with this approach is saying, can I, the same as I learn my coordinates from data, can I learn the equations directly from data? And that is what we're calling the black box approach, and it's basically saying, grab your equation that you will have obtained from the Galerkin projection and just feed it to available data. And that's the black box that we have put Galerkin in a black box. This is very similar to work that is being done by another group at EFRIP, these friends over here. They have already published a paper about that, and I strongly recommend you to take a look. This is a more data-driven approach, so you need less information about the underlying structure problem that you're trying to solve. We have applied this type of emulation to an actual experimental setup where we're trying to control the beam position of a beam of particles as you change the currents that are passing through magnets. And the idea is that through the simulation that these folks are able to use, is called COSI, you have these very high dimensional objects, which are these matrices, thousands of variables. Turns out they live in a very small dimensional space, so you can apply the exact same techniques that we were describing, and the thing just works. You're able to obtain, depending on the number of bases that you use, a very precise determination of where the beam should be through the transport properties, and it's something like around 3,000 times faster than the software that they're using for tuning the beam. So this will allow you to have this online feedback on the experiment while you're running it, to not have to spend hours and graduate students hours calibrating the thing. Okay, I'm almost done. This is the previous to last application, and then is my final conclusion. So it has been a journey. Let me take a breath. Let's talk about applications for approximating posterior distribution, normalizing flows. So remember that I was talking about these distributions that we're interested, the goats told us that we need to model these type of probability distributions. The idea behind this is, can I describe this object with fewer degrees of freedom than just telling you the value of the distribution at each single point? And the idea of what normalizing flows do is to say, I'm going to reproduce this by grabbing a very boring Gaussian. So I'm going to start kind of like with a white state or blank state. And I'm going to try to devise a map that can take me from these boring distributions to the non-boring distribution. We do that through a neural network, and that is what we call this application of the normalizing flow process. And the bottom line of this is that it just works. You can encode the properties of your posterior distribution not on the samples, but on the transformation, the map that takes you from the boring Gaussians all the way to the posteriors that you're after. And this is extremely important, because if we really want to move towards a future in where we can do these continuous calibrations, it will be annoying, even with emulator, to have to run the damn thing every time that somebody goes and measures something. If instead we're encoding the posterior distribution of the models in the weights of the neural network, we can just adjust them as new data becomes available. I'm not going to talk about this because I'm boring myself, but I want to show you this very nice chef galerkin that I have. And if anybody is interested in combining models for predictions, you can ask me later. OK, my final part, lowering the barrier. The point that I want to make with this, and this is the most important part, in my opinion, of the entire talk, is that these type of tools are very, very good to help us lower the barrier and create points of entry for new people to join science. I have 3 reasonings for that. The first one is these things are just widely applicable. You learn about these, and it doesn't matter if you want to apply this to astronomy or turbulence or engineering or finance. It is something that allows you to transcend the boundaries between different sets of groups of knowledge. It's almost self-trainable because there is so many resources online that are amazing that you can just encourage somebody to go and watch a video, to look at the code that is public, such that they can train on these things that are incredibly useful. And the third part, that is exponentially impactful. And this is very funny because this is a paper of people using machine learning to predict how many papers are going to be including machine learning aspects. And the growth is basically an exponential growth. So this is a perfect opportunity for creating a more inclusive and scientific community now. And on the nuclear physics side, that we sat down and wrote this document together, that is one of the first recommendations, or first important, is we need to draw talents of all the people in the nation, I will argue all the people in the world, to be able to advance scientific endeavors. So we're not the only ones pursuing this, but in particular, me, Kyle, and other people in the team have created this collaboration network. And we have, Kyle is a magician. I really don't know how he does it. He created a forum in where everybody can gather together to share this type of resources and encourage each other. We have used it in many, many summer schools and camps and collaborations that we have created for the last year and a half. In particular, the part that I want to highlight is how we can use these approaches to canalize the energy and time that high schoolers, such as Megan or other people that I will talk about in a second, have, so they can start training on all of these aspects, help us with science, and create a better future for them and us as well. So we created this Ascension Scholar Program, that is the name of the collaboration. And we are piloting with something that is called the PIN program. PIN and PAN are 2 programs for high schoolers that are being run at EFRIP at the moment. And basically, it's the idea to give them the opportunity to come, learn about nuclear science, do research, and then go back home and probably be excited about following a career in science. So what we have been doing is latch onto PIN and help the high schoolers that are there with career talks, materials from the statistics and computational side, and research projects. And in particular, right now, we're devising a project with 5 of these high schoolers, Megan included, that is going to be an important contribution for the reduced basis method. Is something that is called the collocation method, that we believe that is going to make it much accessible to everybody to use this type of technique. So it's a high impact project that they are carrying off just by guidance from our side. And with that, I'm going to do perfect. I'm going to even finish before 45 minutes. I'm going to give my takeaways, and then we'll have 15 minutes for questions. I have 2 takeaways. The first one is that these methods, statistics and machine learning, are propelling science towards a new era of discovery, in particular in nuclear physics, but I see it in many other places. So we don't have time to waste. That's why I overwhelm you with all of these resources that we can use. And the second is that this thing could also help us in propelling science towards a new era of inclusion, not to lower the barrier, but basically to blow it off so that people can join us and everybody can feel welcome at the table. And with that, I'm going to thank the people that pay for my lunch, all the people that have been working and supporting me, Jason included, for being an amazing host. And I thank you all as well for listening.